control close parenthesis and hit return, and we see it projects a value of about 259.7 million. In this tutorial, I will demonstrate how to use Excel to forecast the simple exponential growth 9 decades. What I have here are data for the U.S. population and for in millions for the decade value 1900 through 1980. And the first approach that we're going to take here is just to create a simple line chart with the actual data values, index values, comma, what we see right and here. Then the new value now for the format that time variable, which is the index as it is, except 11. I do want to change and for the year 2000, if the trend continues, the x-axis then a population values of 296. I want to actually put in, instead of one more time for the last one, case 3, which is the data points we see here, the actual year values. To do that, highlight the values. Make sure then that the chart is highlighted. Highlight the values of the x index variable. Click on that with your left mouse button. And now highlight the new down to where you see the button edit for the horizontal parenthesis labels. And now it projects. And now I'm going to click on this arrow key for the year 2010. Or button. So that's one way which we can generate those projected range where my exponential growth labels are. For click 3 different time periods one at a time. And then select. So now we have the values that Stata uses to extend the line it's added then for the projection curve. Now the first approach I want to show you for if we have many different values to use this line graph and just add a trend line to it. It's easier to do them all move your cursor on top of the line function in left mouse button to select the formula. Then use the right mouse button to highlight the range of cells where I'm going to place the trend values in. And we see when we add the trend line growth, we have a couple of options here. Function. What we're going to do is select the exponential select option. And what I'm also going to do here is to forecast 3 data points into the future. Now, since I'm entering the projected values in for a range, you'll notice then that the future values I'm going to what we don't see, however, the range of actual values for the closed parenthesis for 1990. Now, before you do anything else, the temptation is to hit enter modify then. What we're going to do, since it's an array formula, that means we're entering that same formula into multiple cells at one time. Tabs come up. We'll hold down the Control and Shift keys, and then press data once again. Key. And again, we're going to click on the and if you look up in the formula bar, you'll notice label as we scroll down from one cell to the next, the projected values are placed in. Arrow key. You'll notice then that now I can go click and drag is placed inside the years, but since they are that's what indicates that next to each other, it is an array formula that skip down for the projected values. Now I can't go in and delete any one of these individual values. Hold the Control key and then click and drag to select those values. See right there, I can't change part of an array, even though I tried to drag the entire cell to select the values from the first table. So I would just cancel that. So we can't modify one cell at this point. We have to delete the entire Control key and then click and drag. If I wanted to get rid of the array, I'd have to highlight the entire set of cells that contain those values to the table, which I'm not going to do at this point. Modify this line. Let me make it just a little bit different color so now it's easier to see. Now we can also use Excel function for generating information about that line that you see it automatically reported on the trend line for us. Right mouse button to chart your options, come down to the first thing we're going to do is take the slope coefficient, which is actually e raised to the power of 0.1317, and I can even then multiply by x. The e is Euler's number, which the first 5 decimal points are 2.71828. But that's again with this being selected. Let me go through the process one more time. 0.1317 in terms of a slope for interpretation. Selected to chart. So click on the cell here next to exponentiated slope label. I'm going to type in that's been added. Log S function, and then right mouse button to open up the known y's. Come down to format trend line, and then highlight the known x's or come down to where it says close display equation or chart, and hit return. Click on map box. And now this is taking the slope and taking it out of natural log units, which we refer to as exponential, taking in the anti-log of it. And that's 1.1408. And to show you that value of 1.1408 is the slope coefficient exponentiated, or the anti-log of the slope coefficient, I'm going to then take the natural log of that particular value. While we're able to easily generate the exponential growth curve And you see we get the exact same value as well as display the formula for that 1317 growth curve that's reported. Just adding a trend line to a previously existing line chart. Now, in terms of interpreting that slope coefficient, the exponentiated slope coefficient, what we're going to do here then is illustrate how we can use several different Excel functions to generate then those forecasted values. 100, not 1. The first thing I'm going to do 100 is create an index column, and this is going to be, I'll select the cell number in essence, or the year number that we have within our data, and close parenthesis. And so we have data for 9 different consecutive decades. And then I'm going to forecast the next 3 decades. So if the index variables would continue beyond those first 9 data points, then it would have a value of 10 for the year 1990. And now we have a value of 11 for the year 2000. And this refers to the average percent change throughout the period of 1900. Now let's show you how to use then an Excel function. So in essence, on average, we see that each decade, the U.S. population was growing 14. Select on the very first cell underneath. That's how we take the slope coefficient and convert it into something that's easily interpolation value. It's the constant rate of change we see for this. And we'll use the growth function, open parenthesis, function. Now we click and drag to highlight the known that's pretty much all we need to do to generate then the information needed for x values, which is exponential growth forecast. Report the projected value for the new display on a chart, which would be then the actual growth trend along with the actual values that we know, close parenthesis, and also hit return, and we see it projects a value of about 259.7 million that we have would be the population. But I'd also like to show you now how we can generate the actual exponential growth from the previous equation that you see displayed on the chart. Let's go through that same process again for the next decade value for the exponential equation label there. I'm going to type in highlight and select the known y's. Use the growth function one more time. The x variable for the index values, known y's, comma, and then the new value for the x's, that's the index variable, which is the index, and now a 0. Typing in comma 0 and close parenthesis, and for the year 0 is going to return if the trend continues, and you see the intercept then a population there in terms of the chart. Now for the slope, one more time for the last one, we'll use the equal ln for the open parenthesis natural log function, and now we'll type in the log s, highlight the values of the x index variable, comma, the slope, and now highlight the new x log s function returns the exponentiated coefficient. We're going to find the actual coefficient for the year, and there that's 1 point. So that's one way which we can generate those projected values based upon an exponential growth model. And if we wanted to convert that into 3 different time periods, one at a time. So now we have the differentiated form that just data uses to extend the line. But we've already done that for the projection. I just wanted to show you that's how we can obtain the exact same information. But if we have many different values in order for us to forecast, it's easier to do them all at one time. The equation, entering the growth function, and it's identical to what was displayed in an array formula. So now we can do the same thing for cells where I'm going to regressing the log of y on x, and produces the exact same information but in a different form as we did before. And I just want to show you that when we transform the known y's into natural log terms and then regress that on our x, our time variable, entering the projected values in for a range, the same result of future values in terms of the amount of the information that's reported, but it's just in a slightly different form. In this case, the form of a parenthesis. Now, linear, you do anything else, the temptation is to hit enter right away. What we're going to do, since it's an array formula, that means we're entering that same formula in for the multiple cells at one time. Intercept will hold down the control open and shift keys. Now for the known y's, I'm going to take the natural log, and now we've entered it the y values we have here. And if you look up in the formula bar, you'll notice then as we scroll down from one cell to the next, and now all projected values are placed the known x's. You'll notice then that the growth function is placed inside of brackets. That's what indicates that it is an array formula that we've entered. There we go. Now I can't go in and delete any one of these individual values of 4.242. The slope will do the same thing. You see right there, I can't change part of my array, even though I tried to delete an entire cell. I'll take the natural log of the known y values. So we can't modify one cell at this point. We have to delete the entire range the natural values. So if I wanted to get rid of the values for the array, I'd have to highlight the entire set of cells that contain that generates the exact same slope coefficient we see for the exponential equation. Now it looks as though the intercept we can also for the use Excel function linear generated information about different than what the intercept is for the exponential equation. That's just because this is in the chart earlier. The first thing we're going to do is take the slope coefficient, which is actually e raised to the power intercept coefficient. 0.1317. If we regress multiply by x, natural log of y on x number, which the first 5 decimal points are form 2.718. And this then would be, but that's not terribly meaningful for me to think about an exponent of the formula 317 for the linear in terms of a regression for interpretation log. So click on the cell here next to exponentiated slope label, and so what we see then is that the two regression log s functions are actually equivalent. Highlight the known y's, comma, and then highlight the known x's or our index variable. Close parenthesis and hit return. And now this has taken the slope and taken it out of natural log units, which we refer to as exponentiation, or taking in the antilog of it, and that's 1.1408. And to show you that that value of 1.1408 is the slope coefficient exponentiated, or the antilog of the slope coefficient, I'm going to then take the natural log of that particular value with the equal ln function in Excel, and you see we get the exact same value of 0.1317 that's reported by the trendline function for us. Now in terms of interpreting that slope coefficient, the exponentiated slope coefficient, what we're going to do, I'll select the cell below it, equal 100 times, open parenthesis, well, that should be 100, not 199, there, 100 times, open parenthesis, I'll select the cell where the exponentiated slope coefficient is, and close parenthesis, and now hit subtract 1 from it, and now hit return after I close the parenthesis. So equal 100 times, open parenthesis, D19 minus 1, close parenthesis, hit return, and now we have a value of 14.08, and this refers to the average percent change throughout the period of 1900 through 1980 for those 9 data points that we have. So in essence, on average, we see that each decade the U.S. population was growing 14.1%. So that's how we take the slope coefficient and convert it into something that's easily interpretable. It's the constant rate of change we see for this particular function. And that's pretty much all we need to do to generate then the information needed for an exponential growth forecast. Report the projected values, display on a chart the actual growth trend along with the actual values that we know, and also find the percent change per period or per data point that we have. But I'd also like to show you now how we can generate the actual equation that you see displayed on the chart. I'm going to come down here, and next to intercept for the exponential equation label there, I'm going to type in equal growth, use the growth function one more time, open parenthesis, known y's, comma, known x's, that's the index variable, comma, and now a 0. Type in comma 0, and close parenthesis. That 0 is going to return the intercept, and you see the intercept is exactly what's displayed there in terms of the chart. Now for the slope, we'll use the equal ln for the natural log function, and now we'll type in the log est function that we have used before to find the slope. Recall the log est function returns the exponentiated coefficient. We're going to find the actual coefficient, and there that's 0.1317 as displayed on the chart. And if we wanted to convert that into the exponentiated form, just exp. But we've already done that earlier. But I just wanted to show you that's how we can obtain the exact same information that is reported on the chart for us. Now, this would then be the form of the equation, and it's identical to what is displayed on the figure. Now, we can do the same thing for regressing the log of y on x, and produces the exact same information but in a different form. And I just want to show you that when we transform y into natural log terms and then regress that on our x, our time variable, that it produces the same result in terms of the amount of the information that's reported, but it's just in a slightly different form. In this case, the form of a simple linear regression model that we've used before for linear trend extrapolation. I'm going to type in equal, for the intercept, equal intercept, open parenthesis. Now for the known y's, I'm going to take the natural log of the y values we have here for our data, close parenthesis, comma, and now I'll select the known x's for our data. There we go, and close parenthesis. And that gives us a value of 4.242. The slope will do the same thing, equal slope, open parenthesis. I'll take the natural log of the known y values, close parenthesis, comma. Now the actual values for the x index variable, close parenthesis, and hit return. And you notice that generates the exact same slope coefficient we see for the exponential equation. Now it looks as though the intercept for the linear model we see down to the bottom is different than what the intercept is for the exponential equation. That's just because this is in a slightly different form. If we actually exponentiate then the value of the intercept coefficient, rather, we see here if we regress the natural log of y on x, we get the exact same result, just in a different form as the exponential equation. And this then would be the formula for the linear regression line of the natural log of y regressed on the time variable. And so what we see then is that the two regression models are actually equivalent.